Hey guys, as you know, being an AAHL student, integration by parts is one of the four techniques that you need to know how to handle when integrating. So you have the power rule, which is the easiest one. You just increase the exponent by 1, divide by that exponent, and it shows up whenever you have a polynomial. You have integration by substitution, which is common to the AASL curriculum. And then you have the two that are strict or strictly taught in the HL curriculum, which are integration by parts and integration by partial fractions. From all of these, the hardest one to identify is arguably integration by parts. You can definitely spot when you have the integral of a polynomial. You can definitely spot the fact that you have a rational function. Now, substitution, integration by parts, they tend to blend a little bit, so you have to think about it a little bit more. For integration by parts per se specifically, you have 4 different types that you should know how to handle. The integrals which require integration by parts only once and then you're done. The integrals that require integration by parts twice. And then you have the ones that involve integration by parts with substitution, which tend to be one of the trickiest ones. And you have the cyclic ones, which are long. They're not particularly hard, but they take a little bit longer to solve, and the idea behind it can be a little bit tricky initially, but then after you go and solve a few exercises of the cyclic type, you get the hang of it. Now, the idea today is that we go through these 4 examples, these 4 types. So integration by parts once, twice, with substitution, and the cyclic one. We're going to use 4 different examples for that. And also we're going to go through how to select what is U and what is dV properly. So let's get to it. I guess it's worth mentioning first where integration by parts comes from. And it comes from the reverse process of using the product rule for derivatives. Let's suppose you have 2 functions, u and v, and both of these are functions of x, u of x and v of x. We're going to represent these functions only as u and v, and we're going to differentiate the product of these 2 functions. So what is the derivative of u times v? Using the product rule, we have the derivative of the first one times the second one plus the first one times the derivative of the second one. And of course, you can illustrate the left-hand side as u times v prime as well. So we can erase this d dx. Now, we are going to rearrange this equation by writing this on the left-hand side, meaning that we have u times v prime equal to u times v prime minus u prime times v. And we're going to rewrite this equation with the right-hand side on the left and with the left-hand side on the right, which doesn't change anything, of course. So we have u times v prime equals u times v prime minus u prime v. Now, what we can do here is to integrate both sides, which means that we're going to integrate this. And of course, for this one, we can split into 2 different integrals, given that the integral of a difference is the difference of the integrals. So we have the integral of u times v prime equals the integral of u times v, all of this prime, minus the integral of u prime v. Now, given that integrating a derivative gives us the function itself, meaning this function right here, which is composed of the product between u and v, or for practical purposes, we can simplify the derivative with the integral. What we have is the integral of u v prime equal to u times v minus the integral of u prime v. And there we have it. This is the formula for integrating by parts. Now, if you have an upper and a lower bound, meaning if this is a definite integral, what we need to change is the following. Let's say that the integral is evaluated from a to b. Therefore, we're going to have u times v from a to b minus the integral from a to b of u prime v. All right, so let's go through the 4 examples. We're going to start with integration by parts once, when we only need to use integration by parts once. The integral that we have is the following. The integral of x times sine of x dx. So a simple example. One thing that you need to establish here, given that we're switching this integral or let me use this as an example, this integral of u times v prime equal to uv minus the integral of u prime v, given that we're switching this for this, which hopefully is simpler. That's the idea, to switch something that's more complicated to something that's simpler. We need to know how to choose what is our u and what is going to be our v prime as a consequence of that. We choose u, and whatever we have left is going to be our v prime. In other words, what is our u in this case? Is it x or is it sine of x? And this choice can make or break your exercise. Now, there's a way to make sure 90% of the time that you choose the correct u. And I say 90% because there's some very creative types of integrals or different types of integrals which require these creative strategies. For example, the integral of ln of x squared. In that case, it's a little bit hard to see. However, let's say 99% of the cases, if you use this acronym, you're going to be fine. The acronym is the following: I late. And it's easy to remember if you just picture you getting to class. You're always late, right? I late. So this is how we prioritize our choice for u. What do I mean by I late? Inverse trig functions, log functions, algebraic functions, trigonometric functions, and exponential functions as the last option. And here are some examples of each type of function. So for inverse, for example, you have arcsine, you have arctan. I'm going to use two different notations because some books use one, others use another. Careful because in this case, careful with the fact that cosecant and secant, for example, these are not inverse trig functions. These are trig functions. So they go in the fourth option, which is trig. For logs, we have, for example, log base 10 of x or ln of x, or for example, ln of x minus 1. For algebraic, we have x squared, or let's say 2x plus 1. These are all algebraic functions. For trig, we have sine of x or cosecant of x. And for exponential functions, we have, for example, e to the x or 2 to the x and others. So using this acronym, ILATE, what should we choose for u? In this case, u is going to be our x, meaning that dv, which is whatever is left, is sine of x dx. Now, we need to calculate from u du, which means that we need to differentiate x, which is just 1 dx. And we need to find v as well, which is the integral of dv, so the integral of sine of x dx, which is negative cosine of x. And using integration by parts, we have u times v, which means x times negative cosine of x, minus the integral of v, which is negative cosine of x. That's why I flipped the sign of this integral, times du, which is dx. And we did, in fact, find an integral which is much simpler to solve, the integral of cosine of x. So we have negative x cosine of x plus sine of x plus c. Now, this is the introductory example, one in which we use integration by parts only once, as I mentioned before. We're going to go to the second type, and let's say that we're increasing the level of difficulty. So the second type is the one that requires integration by parts twice. I'm going to give you a few hints when you face that type of exercise. All right, so let's get to the second type, which is integration by parts twice. We need to use integration by parts twice in this example. What is the example? Let's say we have x squared e to the x dx. In this case, given that from an exponential function and an algebraic one, the algebraic one has a priority for becoming u, and each time that we integrate by parts, the power of this algebraic function decreases by 1, we're going to use it twice. We're going to need to use integration by parts twice. How is that going to look? Let's see. In the first integration by parts, we're going to use u as x squared, given that x squared has a priority, which means that du, which is the derivative of x squared, is 2x dx. Also, dv is whatever we have left, which is e to the x dx, meaning that v is the integral of e to the x dx, which is e to the x. So using integration by parts, we have u times v minus the integral of v e to the x times du, which is 2x dx. And we can also rearrange this and write it like this: -2 or -2 times the integral of x e to the x dx. Now we can see that the power of the algebraic term got decreased by 1. Therefore, we're going to need to apply integration by parts once more so we can get rid of it and only have the integral of e to the x to worry about. Now, let this be a tip for when you're applying integration by parts twice. Given that we tend to memorize the formula for integration by parts using u, v, du, and dv, don't switch. Well, you cannot use lowercase u and lowercase v again because these values are taken. You've already used these variables. Now, what you can do is to use capital U and capital V to keep the formula consistent and in a way that you're referring back to the same two letters, which are U and V. So when we use integration by parts for the second time, we have capital U as x, which means that du is dx, d capital V is e to the x dx, therefore capital V is e to the x. And remember that all of this goes over here. Therefore, and let me color code this, we have x squared e to the x minus 2 times capital U, capital V, minus the integral of capital V, d, and given that this is e to the x, we have x squared e to the x minus 2x e to the x, now plus, careful with this sign right here, 2 times e to the x plus c. And that is it. This is the example of integration by parts used twice. Now we're going to move to integration by parts with substitution, and lastly, we're going to do a cyclic one. All right, so on this third example, we have integration by parts with substitution. Now, this integral is not a trivial one. It's hard to see what should be done, and it's hard to see which techniques should be used. In this case, we have substitution, which will lead to an integration by parts. And it's easier to see the substitution if we break this x cubed in two parts or in two terms. We're going to write x cubed as x squared times x. And I gave it a little bit of space so I can write cosine of x squared in the middle. And then we have dx over here. Now, the substitution that we can and should use is calling x squared something else. And for the same reason that I didn't use other letters which were not u and v for the previous exercise. We used lowercase u and lowercase v, then uppercase u and uppercase v. I want to keep u to be used later, so we still refer back to integration by parts as u, v, or du, dv. Therefore, the variable that I'm going to use to do the substitution is using a. So we can call x squared a, for example. And of course, you can use any other variable. So let's say that a, we're going to use a, is x squared, meaning that dA is 2x dx, which also means that dA over 2 is x dx. And I wrote it like this because we do have x dx over here. Therefore, we're going to have the integral of a times cosine of a times dA over 2. And the 1 over 2 can be moved over here. Now, if you don't want to replace the upper and the lower bounds, that's fine. You can just carry this integral as an indefinite one and then go back to the original variable, which is x. I do personally believe that substituting the upper and the lower bounds at the same time that you do the substitution is better. Therefore, if you choose to do that, do know that you need to replace both the upper and the lower bounds on x over here and calculate what your new a is going to be, or what your new upper and lower bounds, what they're going to be. We're basically squaring these numbers, so we have pi over 2 and then pi over here. And if you do this, you don't need to worry about rewriting the integral in terms of x anymore. Once you finish the integration by parts process and substitute the upper and the lower bounds, then you're done. Speaking of which, how can we use integration by parts over here? We have a mix between an algebraic and a trig function, which means that the algebraic one wins. Therefore, we are going to call u a, meaning that du is going to be dA, and dv is cosine of a dA, meaning that v is the integral of cosine of a, which is sine of a. So we have, and please don't forget about this 1 over 2 over here, we have 1 over 2 times uv, a sine of a. Don't forget to place the upper and the lower bounds over here from pi over 2 to pi, minus the integral from pi over 2 to pi again of v du sine of a dA, which means that we have half times a sine of a from pi over 2 to pi minus negative cosine of a, which is the integral of sine of a, negative cos. And given that the upper and the lower bounds here are also pi over 2 to pi, you can substitute or write both of these upper and lower bounds over here from pi over 2 to pi. Now let's start with the upper bound. So we have pi times sine of pi plus cosine of pi minus pi over 2 sine of pi over 2 plus cosine of pi over 2. And knowing your unit circle, you do know that sine of pi is equal to 0, cosine of pi is negative 1, sine of pi over 2 is 1, and cosine of pi over 2 is 0. Therefore, we have 1 over 2 times negative 1 minus pi over 2, which is the same as negative half minus pi over 4. And there you go. All right, so let's move to the fourth and last type of integration by parts, which is the cyclic one. We not only have to integrate by parts twice in this type of integration by parts, but also something else is going to happen. Now, this type of integration by parts shows up whenever we have, and let me borrow the acronym that we used previously, a mix between a trig and an exponential function, such as, for example, e to the 2x cosine of 3x dx. Now, given that we're mixing the lowest priorities for choosing u, if you're mixing these two, it doesn't really matter what you call u and what you call dv. If you choose your u to be e to the 2x, or you choose it to be cosine of 3x, in both cases, it will work. I'm going to choose u to be cosine of 3x. Therefore, and careful because we need to use the chain rule, we have sine of 3x, negative sine of 3x, times 3. So don't forget about this 3 over here. All of this dx. Now, given that dv is e to the 2x dx, again, don't forget about the chain rule, which means that our v is going to be 1 over 2 e to the 2x, because when we differentiate this and this specifically, we're going to have a spare 2 multiplying over here. So they cancel out and we don't see any 2 or half multiplying over here. There's nothing here. There's just 1. So they cross each other out. Now we have u times v. So half e to the 2x cosine of 3x minus, and this is us already applying integration by parts, minus the integral of v, so e to the 2x times 1 over 2 times du, which is negative 3 sine of 3x dx. Now this can be simplified a lot if we move the constants outside the integral, meaning that we're going to have a positive 3 over 2 integral of e to the 2x sine of 3x dx. Now, once again, and now for this integral, we need to use integration by parts again. And again, we have a mix between an exponential and a trig function. So let's call our u, or capital U in this case, our trig function, which is sine of 3x. meaning that d capital U is 3 cosine of 3x dx. Now our dv is going to be e to the 2x dx, similarly to our lowercase v that we used previously, so v is half e to the 2x. So for that integral in green, we have u times v, sine of 3x times half e to the 2x, minus the integral of v, we can move the half outside, times du, and we can move the 3 outside as well. And do notice that this 3 over 2 is multiplying everything that's inside the green set of parentheses. Therefore, if we FOIL it, we're going to have 1 over 2 e to the 2x cosine of 3x plus 3 over 4 sine of 3x e to the 2x minus 9 over 4 integral of e to the 2x cosine of 3x dx. Now, do notice that what we've been calculating since the beginning or evaluating is this integral right here. So we can copy it on the left-hand side in all steps. And also notice that it's exactly what shows up as the last term in the right-hand side. Therefore, if we move all this to the left-hand side, we are going to have 1 integral of e to the 2x cosine of 3x dx plus 9/4 of the same integral, which is the same as 13 over 4 integral of e to the 2x cosine of 3x dx. Now all that equal to this. And if we divide this whole equation by 13 over 4, we get the integral of e to the 2x cosine of 3x dx equal to 2 over 13 e to the 2x cosine of 3x plus 3 over 13 e to the 2x sine of 3x plus c. Now, this is the last and arguably the most annoying type of integration by parts, the cyclic one. And there you have it. These are the 4 types.